David Hilbert issued a specific mathematical challenge: provide a rigorous foundation for Schubert calculus, the branch of geometry used to count how objects like lines and planes intersect in projective space. Over continuous complex numbers, this theory works predictably. Intersecting geometric varieties produces clean counts represented by Littlewood-Richardson coefficients. But over arbitrary fields, or the ring of integers, the smooth geometry breaks down into pathological singularities, making classical topological counts unreliable. To calculate intersections across any field, mathematics must move beyond topological shapes and derive counts from an algebraic structure that remains invariant under field reduction. The Adelic Langlands Program provides this invariance by mapping the problem onto the Adel ring. The classical Grassmannian is replaced by the Beilinson-Drinfeld Grassmannian, shifting the context from geometry to representation theory. This mapping changes how we define geometric constraints. Classically, they're Schubert varieties intersecting in the Chow ring. Under the Langlands correspondence, these varieties map to local Hecke operators. Geometric intersection becomes the spectral composition of these operators. This transformation identifies enumerative intersection theory with the calculation of automorphic multiplicities, removing the dependence on smooth, continuous geometry. The Satake isomorphism linearizes the problem. It maps the local p-adic operator algebras directly to symmetric polynomials, ensuring the results are governed by the characters of the dual group rather than the shape of a variety. The Hecke-Schubert trace identity makes this explicit, equating the counting of discrete rational points with a spectral trace. The result is exactly the Schur character of the dual group, locking the intersection count to an invariant across arbitrary fields. Think about the classical rule where multiplying two geometric classes finds an intersection count. Using this new translation, how would that operation be expressed algebraically? Geometric multiplication corresponds exactly to the tensor product of two Schur characters. This expansion provides coefficients that are field-independent integers, satisfying Hilbert's requirement for a universal foundation. Adelic decompression explains why these counts remain rigid. The Fourier-Mukai transform takes discrete intersection data, represented here as skyscraper sheaves, and distributes it as continuous wave bundles across a prime fiber. Because the prime fiber is a compact torus, the continuous phase loops are quantized. These quantized winding numbers prevent the intersection counts from distorting or dissipating. This framework must also account for exceptional bad primes, where the geometry degenerates and conductors spike. These moments of ramification threaten to scramble the intersection data. The local epsilon factor acts as a micro-local stabilizer. It injects a phase correction that absorbs the geometric irregularity and counterbalances the singular locus at that specific prime. This mechanism isolates the stress of the singularity to a point source. It prevents informational loss, ensuring the global intersection number remains stable despite localized arithmetic defects. Consistency requires the global product formula. To remain stable, every local epsilon factor phase must balance to 1. If a bad prime shifts the local phase, it triggers an Archimedean counter-rotation, forcing discrete p-adic counts to match the continuous complex numbers. The transition from topology to arithmetic group theory completes in 4 steps. Step 1. Geometry maps to spectral operators. Step 2. The cohomological traces map exactly to Schur characters. Step 3. The discrete points transform directly into continuous waves. And finally, Step 4. Bad primes resolve through global invariance. By anchoring Schubert calculus in the representation ring of the dual group, the intersection coefficients become field-independent integers. Because the global product formula enforces consistency between every prime and the complex numbers, the rigorous foundation for enumerative geometry is complete. Hilbert's 15th problem is solved.